Cumulative distribution functions, CDFs. Cumulative distribution functions, CDFs. Okay, so we've talked a little bit about moment generating functions, and one of the attributes of moment generating functions is that they completely describe distributions. Also, cumulative distribution functions completely describe distributions. For example, here's a distribution for a discrete variable, of course, right? X can take on the value of -1 with probability 20%, or 1 with probability 20%, or it can be 2 with probability 10%, or 3.5 with probability 10%, or it takes the value of 4 with probability 40%. Okay? Let's see. 20%, 40%, 50%, 60%, 100%. Get it? Right? Yeah. Okay. So the cumulative distribution function for any random variable is defined to be the probability that x is less than or equal to some number little x. Okay? This is the CDF, and usually we give it the symbol. We usually use the symbol big F, or sometimes big G, or big H, or big P, or big Q. Not big P, but usually big F. And sometimes we'll denote that we're talking about the CDF for the random variable x by putting a big X down in the subscript. Okay? And it's really a function of little x, but it's defined to be the probability that x is less or equal to little x. This is important. It's a less than or equal to sign. And so we can actually draw this function for this example here. This function is 0 all the way up to -1 there, right? Where x, this is the x-axis. When x takes on the value of -1, this function is actually now 20%, right? See that? There's a jump there. There's a jump there. Got a closed ball there. And then there's another jump here, isn't there? When x is +1, then we jump up another 20%, right? And then we go again. When we hit 2, we go up to 10. We go up by 10%, right? And then we go 3.5 there, up another 10%. Okay, open circle. And then when we get to 4, we jump up the remaining 40%. Fantastic. Look at that. Yeah, so I hope this makes some sense. This is a graph of the cumulative distribution function for this random variable x. Okay. This is the graph of this guy. Okay. All right. Now, discrete random variables such as this are going to have cumulative distribution functions that are step functions like this. Okay. In general, they don't have to look like that. It could be that you have a CDF that looks something like this. It could be 0 for a while, and then it could smoothly come up and go like that, and then there could be a jump like this, and then like that, and then, you know, maybe something like that, and then like that, maybe, and then finally maybe that's 1 up there. Okay? All right? That's also a CDF. It's got some jump positions there. So you know, if this is A, this is B, then what this means is that there is a non-zero chance that this random variable can take on the value of A, and there's a non-zero chance that the random variable can take on the value of B. Okay. Now, in general, CDFs only have to satisfy 2 properties. In general, CDFs, 3 properties, must satisfy 3 properties. Number 1, the limit as x goes down to -infinity of the CDF is always 0. And the limit as x goes up to infinity of the CDF is 1. Okay? Makes sense if you think about it. The chance that this random variable falls to the left of some mark that's way off at negative infinity is going to be pretty small. Should be. And if you move x, if you move farther and farther to the right, such as in either one of these examples, as I move farther and farther to the right, then this function is increasing and increasing and increasing. The chance that I see the random variable take on a value that's less or equal to some mark way off to the right has got to be pretty high, right? So these are sort of properties that we need for these functions to satisfy. The second thing is that these functions are right continuous with left limits. It must be right continuous, that is, continuous from the right. That's what we mean by right continuous. That is, continuous from the right, meaning for any real number a, the limit as x goes down to a of f of x is going to be equal to f of a. Okay, it's continuous from the right, like you can see over here. Okay, for any point as you come toward it from the right, the limit as you approach from the right is equal to the function evaluated at that point. Even here, right? As I approach from the right, it's the limit is equal to the function evaluated at that point b. At any point on this function. It is not, however, left continuous. If I pick any arbitrary point and approach it from the left, the limit is not necessarily equal to the function evaluated at that point, right? You can clearly see as I approach from the left toward the right here, where at the point B, that the CDF evaluated at B is actually higher than the limit as I approach B, right? Okay. So these must be right continuous functions and have left limits. And what we mean by that is as you approach from the left, they have left limits. The limits as you approach any point from the left exist. Okay, so even though it's not continuous from the left, you can find the limit of this function as you approach from the left at any arbitrary point. Okay, the limit of this function as I approach, here as x goes to a from the left is going to be f of a, big F of a, right? Okay, so finally,